What's up? This is Mr. Rodriguez, and today we're going to talk about simple harmonic motion in terms of energy. This is my second video on simple harmonic motion, and we're going to talk about how potential and kinetic energy actually transfer in simple harmonic motion. So, during simple harmonic motion, energy is constantly transferring back and forth between potential and kinetic. Now, the amount of total mechanical energy that we have in a simple harmonic oscillator, which of course total mechanical energy is just your total potential energy plus your total kinetic energy. The amount of this that we have depends on how much work was done to prep the oscillator, okay? And what I mean by that is how much work it actually took to prep the pendulum or to prep the spring, all right? The amount of work that I put in to actually displace it from equilibrium, that's how much total mechanical energy we're going to be dealing with to start off, and that's how much is going to be trading back and forth between potential and kinetic, even though the total energy is going to stay the same the whole time. All right, so hopefully that was a pretty good visualization. Now, because we're talking about energy, I wanted to go ahead and just do a quick recall here really quick. And I wanted to remind you that, and this is actually misspelled, don't laugh at me too much, this should be joules. All right, I wanted to remind you that work and energy both use the units joules, all right? So that's capital J. And that work is defined as force times distance, all right? It's a scalar multiple, it's force times scalar distance, all right? And that typically feeds how much energy you're dealing with. But I also wanted to remind you that potential energy is defined differently based off of which conservative force we're dealing with. So we're talking about simple harmonic motion here, and simple harmonic oscillators can be in a pendulum or they can be on a spring. And the restoring force is different for those two. So the potential energy could be gravitational potential energy, or it could be elastic potential energy. And so for a pendulum, the gravitational potential energy is mgh, mass times acceleration due to gravity times however high from our lowest point we are. And by definition, elastic potential energy is derived from Hooke's law, and it's 1/2 kx squared, where k is the spring constant for whatever spring you're dealing with, and x is just your distance from your equilibrium, or the natural length for the spring. All right. Another thing we're going to be doing moving forward is we're going to be calling potential energy capital U, which is pretty much universally accepted for potential energy, and we're going to be calling kinetic energy capital K. Instead of just capital PE, capital KE, it's going to be U and K. Now, let's say that you have some mass spring system set up horizontally on a frictionless surface. We're typically going to define our frame of reference in which x equals 0 at the mass spring system's equilibrium position, the position where there's no restoring force acting on the mass. The spring is at its natural length. All right. Now, what's going to happen is if I were to displace this mass some distance to the right or some distance to the left, such that it was no longer at x equals 0, but was now at x equals x, or x equals negative x, then, according to Hooke's law, there will be a restoring force that points towards the equilibrium. Now, as it points towards the equilibrium, this block will accelerate towards the equilibrium, and there's nothing to stop it at the equilibrium. So it's going to keep going past until, in this case, Hooke's law starts to bring it back in the other direction again. And this is why we have simple harmonic motion, all right? We end up just going back and forth between our two maximum displacement points, all right? And so it's in this motion that kinetic energy and potential energy continuously swap back and forth with each other. So which one, like what happens where? Well, you'll understand that if I were to pull this mass some distance x and set it here, there is potential energy due to Hooke's law, or the restoring force, equal to 1/2 kx squared. All right. So if I am holding it here, then there's potential energy because that restoring force wants to push it back to equilibrium, and the potential energy that it's experiencing can be found using 1/2 kx squared. The moment I let it go, it is going to start moving and accelerating towards equilibrium. And that potential energy is going to begin to convert to kinetic energy, all right? And so it's going to convert to kinetic energy all the way until it reaches its equilibrium position. It will have some negative velocity, and I say negative because it's going to the left, it will have some non-zero velocity. So it will have at this point some level of kinetic energy, because don't forget that kinetic energy is 1/2 mv squared. Of course, the mass isn't zero, and if the velocity is also not zero, then we have kinetic energy at this point. In fact, we have kinetic energy everywhere in between our maximum displacement points, but it's going to be at its maximum velocity and maximum kinetic energy as it's passing this equilibrium point. Because the moment it passes this equilibrium point, then the restoring force is going to want to cause it to go back towards that equilibrium point again. So it's slowing it down all the way until it gets here, until it starts doing the same thing over again, but in the opposite direction. So what I'm trying to tell you is that generally, here's how the energy will oscillate. At x equals plus or minus x max, potential energy will be at its greatest. At x is equal to 0, potential energy will be 0. All right, because at the x equals 0 position, there's no restoring force, so there's no potential energy. This is also true for pendulums. All right, so at that point when there's no potential energy, the kinetic energy is at its maximum. Now, of course, by the conservation of mechanical energy, K plus U is equal to some constant. So as potential rises and falls, kinetic energy also rises and falls. But one thing I want to make sure that you understand is that the energy exchange is not linear with respect to either position or time. So think of this as, instead of theta here, think of this as x, okay? What I'm saying is that these far edges over here, they represent the maximum displacement, the negative x and positive x, where our potential energy is at its max, our kinetic energy is basically 0. And when they're transferring, they're not transferring in straight lines, okay? They're not transferring in linear relationships, okay? They're transferring with these parabolas, right? So that means that you can't just take the halfway point in position and expect that to line up with a point in which they've equally traded half of their totals, okay? So the point in which they cross is not actually the halfway point in the displacement, right? So that's just something to keep in mind, right? It's not really within the framework of algebra-based physics 1 to quantify what's going on here, but as long as you understand that this is not a linear trade-off. So let's work an example here. Let's say there's a block of mass 5 kilograms, and it's oscillating on a spring whose force constant K is 500 newtons per meter. All right. Now, the amplitude of the oscillation is 4 centimeters. Now, if you remember anything from the last lecture, you'll understand that amplitude represents the maximum displacement from equilibrium. So we're going to go ahead and calculate the maximum speed of the block. So there's one thing we have to be able to conceptualize here. We have to know that the maximum potential energy is equal to the maximum kinetic energy. Yes, they occur at different points, but the maximum kinetic energy for the system is equal to the maximum potential energy. That said, I can go ahead and say that 1/2 kx squared, because that's elastic potential energy, as long as we're dealing with our maximum displacement, is equal to 1/2 mv squared, as long as we're dealing with our maximum velocity. And that's great because that's what we're looking for, maximum speed of the block. All right, we have everything we need here to find velocity. So I'm going to go ahead and cancel out these 1/2s because I have one on each side. I'm going to divide both sides by my mass, and I'm going to take the square root so I can isolate velocity. All right, so I'm going to be left with the square root of kx squared over m. This should give me velocity. I have everything I need in here to go ahead and solve that. I'm going to go ahead and plug in 500 newtons per meter for k, 500 newtons per meter for k. We're going to multiply this by 0.04 meters, 0.04 meters squared. That's my maximum displacement because that's my amplitude. And I'm going to divide that by m, which is given as 0.05 kg. All right, if I go ahead and plug that all into a calculator, I should come up with just 4 meters per second. All right, great. So there is this interesting topic about effective spring constant, and it can pop up on certain exams, on certain types of Physics 1 courses in which you have a simple harmonic motion problem, but it's with a mass spring system. The thing is that there's more than one spring. And I just want to let you know that this doesn't change anything about how we solve simple harmonic motion problems, as long as we know what to plug in for the effective spring constant. Because having 2 springs is obviously going to make the spring constant different than if you just had 1 spring. So I wanted to talk about 3 different setups in which you can go ahead and I can go ahead and let you know what the effective spring constant is for this setup. And you can go ahead and keep that in mind so that you can use it in the future if you ever see a simple harmonic motion problem in which you have multiple springs and you're not sure exactly how that changes the problem. Well, I'm telling you now, it doesn't really change the problem. In this setup, as long as you know that your effective spring constant, okay, is equal to K1 plus K2. So everything works the same. All the equations and relationships you're used to will work the same. But instead of just K1, when you're plugging in for K, any equation that has K in it, you're going to plug in whatever the spring constant for the first spring is plus whatever the spring constant for the second spring is. So your new effective spring constant is K1 plus K2. And what's really cool about this second setup is because Hooke's law works in both directions, you have the same amount of force applied whether you want to stretch a spring X distance from equilibrium or compress a spring X distance from equilibrium. So these two setups actually work exactly the same way. If I pulled the box of mass M to the right here, both springs are pushing back in this direction. The same is true here. If I push this box to the right here, some X, both springs would be pushing back to the left because this spring wants to go back to its equilibrium length, whether it's stretched or compressed, and so does this one. So they'll both be pushing back in this direction. That said, in this setup, the effective spring constant is equal to K1 plus K2. All right, so just keep that in mind. Now, there's one more that's a little bit trickier. In the notes here on this screen that you can download below, there is the derivation for how this next one works, but I'm going to go ahead and just tell you what the effective spring constant is. And if you want to look at the derivation, you're more than welcome to do so. You can download the notes right below. That said, if you have a situation in which you have some mass and it's attached, it's sitting on a surface, and to the left of it there's a spring, and then connected to that spring is another spring of a different spring constant, and then it's all connected to a wall, then the effective spring constant that you're going to have to plug in for K for all the other all the relationships that deal with K, like potential energy and such, is K1 times K2 over K1 plus K2. And this is an interesting one to derive. It's not all that complicated. If you wanted to do so, you can look at it below. I'm going to pass by it really quickly. Now, to summarize, we have a quick table here, and it tells you when things like the restoring force, acceleration, potential kinetic energy, and speed are all at their zeros or at maximums, right? So at the points in which we have a maximum displacement, whether it be positive or negative, then our restoring force, like we said before, is at a maximum. Our acceleration is going to be at a maximum. Now, these could be positive or negative, but they will be at maximum magnitudes. Our potential energy are at a maximum. All right, our kinetic energy is at 0 at these points of maximum displacement when x is equal to our amplitude. And our velocity or speed will be at 0 at these points of farthest displacement from the equilibrium. But when we're at our equilibrium, the magnitude of the restoring force is 0. The magnitude of our acceleration is 0. Our potential energy is 0. Our kinetic energy is at a maximum, and the magnitude of our velocity is at a maximum always. This applies for all simple harmonic oscillators, whether it be a pendulum or a vertical or horizontal mass spring system. So we've been talking a lot about the horizontal mass spring system. What's different about the vertical mass spring system, okay? Spring block system, whatever you want to call it. When you have a block attached to a spring, gravity causes the oscillator's equilibrium to no longer coincide with the spring's natural length, okay? So naturally, a spring has a natural length. If you have it hanging vertically and you attach a mass to it, then that mass is going to stretch it some distance downwards. The question is, how far does it stretch it? It's pretty simple, because the reason why the mass stretches the spring is because the force due to gravity on the mass. So we'll hit an equilibrium point when that distance that it gets stretched actually causes Hooke's law to match force due to gravity. Remember, Hooke's law is negative kx, so it depends on that x, how far it's being stretched. So as soon as that x reaches a point in which negative kx is equal in magnitude to mg, then we have our new equilibrium point. So if we just set kx equal to mg, which we've done right here, kd is equal to mg, that x or d both just stand for how far the spring is being stretched, then we can really easily find how far it was stretched before we reached the equilibrium point, because if KD is equal to mg, we can divide K by both sides, and then we can solve for that distance it was stretched, by just taking the mass of the block times acceleration due to gravity and dividing it by the spring constant of the spring. All right, so let's go ahead and use that in this next example. A block of mass m, which is 1.5 kilograms, is attached to the end of a vertical spring with force constant 300 newtons per meter. So K is equal to 300 newtons per meter. After the block comes to rest, it is pulled down a distance of 2 centimeters and released. What is the frequency of the resulting oscillations? Well, this is two parts here. The first question is, what is the frequency? The second part is, what are the minimum and maximum amounts of stretch of the spring during the oscillations of the block? Okay, let's go ahead and tackle part A first, because we know exactly what relationship we need to use here. We know that the period of a spring block system is equal to 2 pi square root m over k. We learned this in our last lecture, and we'll use it a lot in these simple harmonic motion problems. All right, and what's great is that we know the mass of the block and we know the spring constant k. So I can just go ahead and plug everything in here. 2 pi, and then for m I'm going to do 1.5 kg. For k I'm going to do 300. All right, newtons per meter. All right, newtons per meter. And if I go ahead and plug this into a calculator, then I should get something like 0.44, somewhere around there. This is going to be seconds, but we're not actually looking for period. We're looking for frequency. And if you remember from the last lecture, I reminded you that frequency is actually the reciprocal. All right, so it's frequency is 1 over the period, and period is 1 over the frequency. So all I have to do is, if I know that frequency is equal to 1 over period, then I can just take my 1 and put that over 0.44. So we're going to end up getting something like 2.3 hertz, 2.3. And the units are 1 over seconds, but instead of saying 1 over seconds, we call them hertz, capital HZ. Now for part B, it's asking how much the spring is stretched. So in order to know how much it's stretched as it's oscillating, we're going to need to figure out how far away from its natural position is its equilibrium point. All right, so its equilibrium point is going to be given by D is equal to mg over k. All right, and then we have mg and k, so I can just go ahead and plug in everything here. 1.5 kg, 1.5 kilograms times, let's use 10 for gravity, 10 newtons per meter for gravity for simplicity. I'm sorry, it's not newtons per meter for gravity, right? It's newtons per kilogram. And then we'll go ahead and divide that by 300 newtons per meter. All right, if I plug this into the calculator, I should get something like 0.05 meters. All right, so 5 centimeters. So that means that when we attach the mass to our spring, it's going to drop 5 centimeters, and that's going to be its new equilibrium position. But then the question tells me that I'm going to go ahead and pull down an extra distance of 2 centimeters and release it. So that means it's going to be oscillating with an amplitude of 2 centimeters about an equilibrium position that's 5 centimeters stretched. And so that means that at its maximum stretch, it's going to have 7 centimeters. So at its maximum stretch, so basically the stretch is going to be plus or minus 2 centimeters. So at its maximum stretch, we have 7 centimeters from its natural length, and min we have 3 centimeters from its natural length. All right, and if that was a little bit maybe too quick, then I have a visual that can help us kind of understand what's going on here. First off, here we had our spring that was at its natural length and nothing was attached to it, and then we attached a mass to it which caused it to stretch 5 centimeters, causing this to be the new equilibrium position. Now from there, we went ahead and grabbed that mass and pulled it down another 2 centimeters to start some oscillation here, but with an amplitude of 2 centimeters. So it was coming down here, bobbing back up all the way to here, and then dropping back down. And due to its simple harmonic motion, it was just going back and forth between an amplitude of 2 centimeters. So from there, we can very easily say that, well, if that equilibrium position was at 5 centimeters, then as it was going 2 centimeters up, at that point, it was stretched only 3 centimeters. But as it was hitting its 2 centimeter downward amplitude, then it was stretched at a maximum of 7 centimeters. And that's what we calculated up here. So one more thing I wanted to talk about in this lecture was about pendulums, specifically simple pendulums. They're just a weight of mass attached to a string or a massless rod that swings frictionless about the vertical equilibrium position. Now, the restoring force for a pendulum is not the elastic force or brought to us by Hooke's law or anything like that. It is just gravity. But part of the component to gravity that's pulling it towards, or that the part of the gravity that the actual mass at the end of the pendulum experiences is being canceled out by tension in the rod or string. So there's only the component of gravity that's perpendicular to that rod or string that is actually restoring our mass to equilibrium. This image will help us see exactly how that works. So of course, gravity is always pointing straight downward, but the component to gravity, specifically mg cosine theta, based off of this image you can see here, because cosine is always going to be adjacent to the angle that we're discussing, mg cosine theta, let me write it here, mg cosine theta is always going to be canceled out by the string, okay? So it's basically like canceled out by normal force. So then that means only the component of gravity that is perpendicular to this string is going to be restoring our mass to equilibrium. And so that's always going to be mg sine theta. And it is true that the further we displace our mass from equilibrium, the more of gravity is going to be put into, the bigger a component of gravity mg sine theta will be. All right, so that's how that works for, that's how the restoring force works for pendulums. And hopefully that's good enough information. There's practice problems for this lesson. There's solutions posted. Good luck studying and practicing, and I'll see you guys in the next one. If you have any questions, go ahead and leave a comment below.